Hi, everyone. My name is Daniel Hoffman. I work for Recondo, and today I'll be discussing a case study that we conducted over the past year or so regarding airport parking shuttle operations using PT lines and Viswalk. I'll try to go through this as efficiently as possible so we can get on to dinner because I'm sure you guys are pretty hungry. As for the overall project scope, the main goal of this project was to determine the optimal shuttle operation for a new terminal opening at the airport. We wanted to ensure there was pedestrian connectivity between the airport and the parking facilities on opening day and beyond. We also wanted to confirm that the existing fleet provided enough capacity to support the peak day and off-peak demands. In this case, it meant that no passengers would be left behind by a shuttle. The airport also asked us to consider some cost savings, so we wanted to use as few shuttles as we needed and also reduce the overall distance that the shuttle had to travel to save a little bit on fuel as well as potential servicing. And then they also wanted us to provide detailed videos to provide a more visual understanding. They were a very visually inclined client. So we spent a lot of time introducing hundreds of 3D static models, producing some other smaller simulations of parking facilities that weren't a part of the actual analysis, just to make the visuals really pop. As for background for the standard analyses we do at Recondo, we typically model, we model airport land sides, and typically our Vissim models focus on the roadways surrounding parking facilities. So we typically don't prioritize the actual parking shuttle operation within the facility and treat the airport parking lots as sinks and sources in which there's a vehicle input at the source of the parking facility. To source these sources, for lack of better words, we generally use static analyses to account for pedestrians. However, this does not account very well for variations across a peak hour in pedestrian demand. For example, there may be some influxes in pedestrians that occur at any given time, which can heavily affect the capacity of a shuttle. Some project-specific modeling elements that we included for this project included public transit lines. This was to incorporate pedestrians into the analysis with a seamless connection with Viswalk. We also included vehicle-actuated programming in order to allow PT lines to loop effectively. We found that if they are on a closed network, the PT line will not be able to pick up the shuttle as it completes its loop. So when it passes a PT stop, it does not stop at the stop once again. We also included attribute modifications to further customize these PT lines, which we'll discuss later, and 3D information signs just to provide a little bit more clear data insights during the visualizations in the videos. Some of the modeling assumptions that we used were 8 shuttle 40-foot buses, and the airport had 8 of them with a 35 sit-stand capacity. However, the airport wanted us to be very conservative with this since it is an opening day operation. They wanted to ensure there were no hiccups throughout the any peak hour. So they wanted us to be conservative on this capacity. We assumed that headway management would occur, and it would occur within the parking facilities. In this case, if a shuttle headway was to collapse, the shuttle operator would hold within the lot in order to regenerate the headway. On the other hand, if the headway is not met, like a maximum headway is not met, then an additional shuttle will be deployed into the network to alleviate any issues that may occur. As for how we develop the effective capacity of the shuttle, we effectively assigned a pedestrian size to a particular pedestrian type. For example, a pedestrian with no bag would have an effective pedestrian count of 1, meaning they won't have any additional space that they take up on the shuttle. However, ADA or handicapped pedestrians will have an effective capacity or an effective pedestrian count of 4. This is because they generally have either a wheelchair or other bulky mobility assistive devices. So they take up a little bit more space and also may retain their luggage a little bit as well. We applied these to a pedestrian distribution in order to determine the overall effective capacity, and we had a similar analysis for the effective boarding time. As for how we seated the actual pedestrians into the network, we assumed that the primary parking entry occurred on the east side of the parking lot, which allowed us to determine that the portion of the parking facility that had the highest number of vehicles in the parking facility prior to the peak hour was in zones 4A through 4P, as well as southern portions of zone 3. And this went into our overnight parking seating. We also had a distribution share, which provides the actual pedestrian distribution throughout the peak hour, in which we assumed that pedestrians would travel generally from south to north, as well as from east to west. Because of this, zone 1 or stop 1 would have the highest overall pedestrian share, meaning that there are the most pedestrians at this shuttle. And finally, stop 2 had the fewest number of pedestrians because this is almost more of a seasonal stop. They will only really open this portion of the lot if they need to, and this stop may not even be used in the analysis or in the actual shuttle operation. So as I kind of touched on in the last slide, we have 5 total stops within the surface lot facilities. However, there are variations that may occur throughout the year based on the overall airport demand. So stop 2 or potentially even stop 5 may not be included in any in one of the months of the year. We also had pickups and drop-offs at the terminal curbsides. However, these were on separate curbs, so they required a recirculation from the departures curb all the way to the arrivals curb. And this is one of the ways that we were able to reduce the overall cost of the shuttle operation based on the recirculation route we chose. As for the Vissim and Viswalk geometry, to begin, we started with just general links and PT stops to generate the bus drive aisles within the parking facilities. If you can see in the top right corner, there are additional links running north to south, and this is actually just part of our parking lot that we introduced just to provide a little bit more visualization into our video. Then we included PT stops along the lines to act as the pickup and drop-off locations. These were the bus shelters, and then along the terminal curbsides. We then introduced PT lines to simulate the parking shuttle. Typically, we just use vehicle inputs and static routing decisions in order to do these operations because we aren't focusing on the actual stations or bus stops within the lot. So that is normally enough for the type of work that we do. But for this, the passengers and pedestrians were one of the primary focuses of the client. PT lines use departure schedules, as many of you guys know. They work as kind of as the vehicle inputs, however they operate differently. They release the shuttles at different times, or at a pre-specified time. In this case, we split the departure schedule into 2 different sections. One was the seating period, in which we actually set the base number of active shuttles in the shuttle operation to be deployed to the network. In this case, we had 6 to achieve typical headway of around 3.5 to 4 minutes. And then after that, we have the post-seating period. Essentially, these shuttles are just lined up in a queue in order to dwell behind a VAP-controlled signal head. They'll dwell off the network on a hidden layer, so they aren't viewed. But this just allowed us to provide a continuous shuttle loop using the VAP. We also assigned an occupancy of 2 at the beginning just as a tentative number, but we adjusted these dynamically using attribute modification. As for our VAP setup, as I mentioned previously, PT lines struggle to loop effectively without additional assistance from other components. So because of this, we didn't actually connect the destination link and the entry link because we just wanted the vehicle to run off the network. Otherwise, the vehicle would circulate the network without any real mission, kind of just with chicken with its head cut off. As for the VAP itself, it was coded to release a new shuttle upon the completion of the previous shuttle's loop. Simulates the same shuttle, but it uses a different vehicle in Vissim. And then just for like a visualization thing, we assigned the PT generation and the signal head on a hidden link. As for how our VAP code actually worked, essentially we're starting with asking if the seating period is active. If the seating period is active, then the signal head will remain green, and this is kind of the base configuration for the first portion of the VAP code. Once the seating period concludes, then the signal head turns red as the secondary base condition. And this is the kind of starting point for the second half of the VAP. After that, we're asking if the minimum headway is met. And if it is not, then the signal head will remain red. If a shuttle were to arrive at this point, it means that the headway has collapsed. So we ask the driver to hold within the lot in order to try to regenerate that headway. And then if the minimum headway is met, then the VAP code determines if the detector is triggered, meaning a shuttle is coming to the conclusion of its loop. If it is, then the signal head will turn green momentarily to allow the next shuttle to take its place and continue on to the next pickup and drop off location. And if it is not triggered, then we ask if the minimum or the maximum headway has been exceeded. And if it is, then an additional shuttle is released into the network to alleviate any impacts of the extended headway. If it is not, then the signal will remain red and this loop will continue. This is kind of how our VAP worked. You can see a shuttle completing its loop being replaced by a new shuttle. Might be able to spot where it actually does pick up the next shuttle. And this kind of varies depending on the speed of each of the vehicles, the incoming and outgoing vehicle. But something that we can also potentially adjust using attribute modifications to ensure that the shuttles have the exact same speed as they're passing the same point. Next, we included some attribute modifications for the shuttle occupancy. For this operation, it was a single shuttle operation. So pickups and drop-offs occurred at both the departures and arrivals curbs. So that means that passengers will likely be coming into the parking facility. I'm not sure if you can see, but in the top right corner, the shuttle that's waiting at the stoplight, the VAP controlled signal has an occupancy of 4, but the shuttle that's entering the lot has an occupancy of 1. We need to ensure that these have the exact same occupancy to ensure that all pedestrians are accounted for on the next loop. To do this, we used a 3-step attribute modification process in which we determined if a shuttle was leaving the network, meaning that it was coming to the conclusion of its loop. If it touches the destination link, then the shuttle exit attribute is set to 1. We then use a table lookup to search for the occupancy of the shuttle that has the shuttle exit attribute set to 1, and then we apply that to the shuttle that is sitting on the entry link. And this is how the operation works, and also why we have the shuttle on a hidden link, because we don't want a rear end collision within the lot. Don't want to show that to the client. But you can see the occupancy of the vehicle coming in and going out are both 1. Once we have that set up, we included our pedestrian areas. Most of you guys are pretty familiar with these at this point. We just included walking area, a waiting area, platform edge to connect the Vissim and Viswalk effectively, as well as the input areas and the exit areas. So it's a pretty simple Viswalk network. We had one of these for each of our shuttle stations. And then we included pedestrian routes from the pedestrian input location to the waiting area, as well as from the platform edge to the exit. And you can see how it looked in both 2D and 3D on the screen here. This is what our pickup and drop off operation looked like within the lot. This is stop 1 of the parking facility. You can see there's a net 3 gain on that shuttle. However, these 3 people are probably a little upset that the bus drove off without them. We found that the shuttle operation only really recognized the pedestrians that were waiting on the PT waiting area. So the pedestrians that came in a little bit late weren't actually recognized. And because of this, we didn't include these as passengers left behind because they never really had a chance. But this could be something that we can refine further, potentially with attribute modifications, depending on the capabilities that we're able to determine. As for how we used different Vissim outputs, we used pedestrian record to determine the overall number of passengers left behind by any shuttle. To do this, we essentially just took the PT line behaviors on the waiting area to determine how many times a pedestrian approaches the shuttle. If they're approaching the shuttle more than one time, then they are left behind. And we counted that in kind of a little bit of a matrix using Excel manipulation. We then used vehicle records to determine the average headway and shuttle occupancy at each stop, as well as area measurements to determine pedestrian density, level of service, the number of pedestrians waiting at any given time, things like this. And we used pedestrian network performance, vehicle network performance, as well as vehicle travel times to provide insight to our client. Our shuttle operation worked pretty well. We found that the longest average waiting time at a bus shelter is around 3 minutes, and the longest time that a pedestrian will have to wait by the time they get to a shuttle to get to the terminal is around 11 and a half minutes. This is pretty quick, and the client was very pleased to hear that their existing shuttle fleet was sufficient to provide this kind of operation because they're very focused on providing the best level of service that they can, especially since this is for the first day of the new terminal. We found that a headway of less than 4 minutes is ideal to ensure that the passengers are all picked up. However, we did find that there were a couple instances, I believe it was 2 throughout the entire peak hour, in which one pedestrian was left behind by a shuttle. These were primarily due to pedestrian surges, as well as pedestrians not getting off the shuttle at the to make room. However, this is using an effective capacity of 25 pedestrians, so it's more than likely that these pedestrians would be able to get on the shuttle, especially considering that the average shuttle occupancy approaching the terminal was only 17 passengers. Based on this, we determined that there are 6 shuttles that were required to begin the operation, with a 7th waiting to be dispatched at any given time. And yeah, thank you. And open